We're looking at a test for a new herbal drink blend, and there are 4 judges that are going to taste the 2 drinks. And we want to know the probability distribution for X equals the number of judges that vote in favor of the new blend. Now, we're saying that both blends are equally impressive, so our expectation would be that the probability of success is 0.5. That being said, we can figure out later, if all 4 judges vote in favor, then that would convince us otherwise, and we might say, you know what, maybe they're not equally impressive, but our assumption is, it is anticipated that this is the case. So we want a probability distribution for this. Now, X can be one of 5 values. 0 can vote in favor, 1, 2, 3, or all 4 can vote in favor of this new drink. So now we want to know the probability distribution. How likely is it? Well, for 0 successes, that means out of the 4 judges, 0 will favor it. 50% chance of success, 0 successes. 50% chance of failure, 4 of those assumed in this case. For 1, we would have 4 judges, 1 votes in favor, so 1 success and 3 failures. Then for 2, we would have 4 choose 2. There would be 4 choose 2 ways to have 2 judges vote, because remember, the first 2 can vote in favor, the last 2 can vote in favor, the middle 2 can vote in favor, the middle and the first and the last one can vote in favor. So there are multiple ways this can happen, and that's just keeping in mind what this coefficient stands for. And then 3 and 4, we would do the same thing, except 4 choose 3. These powers go up, these powers go down. So once we have this built, here's what it looks like. So here are the probabilities that we would get, and here's the corresponding probability distribution. So what do we notice first of all before we do anything else? Well, it's very unlikely that either 0 or 4 judges vote in favor. About 6.25% of getting either no judges or all 4 to vote in favor. So that's a good thing. At least for the 0 case, we probably would get at least a couple who would vote in favor. In fact, it would be most likely to get 37.5%. There's 37.5% chance that exactly 2 of them would vote in favor. But really, what do we care about? Well, we don't necessarily care about exactly 2 judges voting in favor. We would just want the majority of them. So the probability that at least 2 of the judges prefer the new blend would be something that would be more mathematically interested in. That way we could say, hey, you know what? There was this probability, we got 4 out of the 4 judges to vote in favor of it. So really what we're looking for is the probability that the random variable is at least equal to 2. So what would that mean? That would mean x equals 2, x equals 3, or x equals 4. So I'm going to do equals, since I'm using a spreadsheet here, this plus this, and I get a 0.6875 probability. So that's pretty good. So I would expect that if these were equally impressive, that about 69% of the time I'd get at least 2 judges to vote in favor. That being said, the probability that we get less than 2 judges would be 0.0625 plus 0.25, which would be 0.3125. So this would be 0.3125. So either 2 or more vote in favor, or less than, this should be strictly less than 2. Or 31.25% chance that you get less than 2 judges voting in favor. And what is the expected value of this distribution? Well, since we have a binomial experiment, this is going to be n times p. Well, if you have 4 judges and you expect 50% of them to vote in favor, that would mean we'd expect on average that exactly 2 judges would vote. And that makes sense because that has the highest probability.